Now we're ready to talk about power series. This is now officially material from 7.4. Okay, so now we're ready to talk about power series, and a power series is any function of the form c sub n times z minus z naught to the k, where k goes from 0 to infinity. So this is very similar to what we do in Calc 2 when we talk about power series. The only difference here is that, of course, z naught and each of the values c0, c1, c2 are all complex numbers, right? Of course. So that's our power series. And what we're going to do is we're going to talk about all the different properties that we have for power series. But before we do that, let's talk about an example. So, or three. So let's look at the function. Actually, the function that we saw in the previous video, z over 2 to the k, is a power series centered at 0. And just so that we can recognize that this is still of the form like I wrote above, this is 1/2 to the k. So that's my c sub, I'm mixing n's and k's here. That's terrible. Let me just call that k. But this is our c sub k. And then this is z minus 0 to the k. Okay, so really it is a power series like this. Our c sub k is 1/2 to the k. Z minus z naught to the k is z minus 0 to the k. And we know that this converges, so we just saw in the previous video that this converges absolutely on the set of complex numbers where the modulus is less than 2. Okay, so that's the first example. The next example we could talk about is, let's think about something like the sum of, as k goes from 0 to infinity, z to the k over k factorial. This, of course, should be very familiar. This is, of course, e to the z. By the way, the previous example also should be familiar. I should add in one thing here. Let me pause on this example. Sorry for that. Sorry for the abruptness of the stop there. But this actually, not only do we know that it converges absolutely, but we actually know a little bit more. This converges absolutely to the function 1 over 1 minus z over 2, which is nothing more than 2 over 2 minus z. Okay, and that absolute convergence happens on the set of complex numbers. It happens on the disk of radius 2 centered at the origin, right? This is just the disk centered at 0 of radius 2. Okay, so not only do we know it converges absolutely, we know what it converges to. So next, let's look at f of z is z to the k over k factorial. And of course, this converges to e to the z. And this is valid on the entire complex plane. So this is a completely valid expansion. It's centered at 0 again, completely valid on the entire complex plane. If I were to look at, say, f of z is, I'm just going to pick another silly example like the first one, z plus 4 over 3 I to the k. As k goes from 0 to infinity. This is going to converge to, so this is again z plus 4 over 3i. That's something like t to the k, but it's going to converge to 1 over 1 minus z plus 4 over 3i. And that'll converge whenever the modulus of z plus 4 over 3i is less than 1. So that tells you that this is going to converge when the modulus of z plus 4 is less than the modulus of 3i, which is 3, or on for z in the disk centered at radius, centered at -4 of radius 3. Right, so this is some disk centered at 1, 2, 3, 4 of radius 3. Okay, so something like that. So as long as we're inside, let me draw a slightly lighter color inside. So this is going to converge inside that disk. Okay, that's the region of convergence there. And then one final example. If we take the series, so the sum from k equals 0 to infinity of, say, k squared plus 1 to the k, z to the k, this is going to converge, and let's think about what this will be equal to. The only value that we're going to get is when, yeah, this will only converge if z is equal to 0. And if z is equal to 0, the only term that's going to be valid is the first one, because whenever you have a power series, let me just back up for 1 second. Whenever you have a power series, c sub k, z minus z naught to the k, so k goes from 0 to infinity. This is c0, because z minus z0 is to the 0 power is 1, plus c1 times z minus z naught, plus c2 z minus z naught squared, and so on. And so we make the convention that 0 to the 0 in the context of power series is 1, because we include that c0 term. Okay, so this is going to be just the first term, what happens when k is equal to 0, and that's going to be 1 to the 0, which is just 1. So this happens only when z is 0. Okay, so these are all examples of power series. Now, what's going to be true for all power series, and I'll call this a proposition. So what's going to be true for all power series is given any power series, call it c sub k, z minus z naught to the k, there's going to exist, so there exists a capital R. It's going to be greater than or equal to 0. It's a non-negative real number, or it's also possible that R is infinity. I'll explain what that means in a second. Here, capital R, I just mean the radius of convergence, but such that the following happens. So the first thing that's going to happen is that F converges absolutely whenever z minus z naught is less than R. F diverges if the modulus of z minus z naught is strictly greater than R. This entire proposition is inconclusive when the modulus of z minus z naught is equal to R, so anything can happen there. And a little bit more, so this is the part that's going to be new to you probably, and this is similar to what happened in one of the previous examples, but F converges uniformly if the modulus of z minus z naught is less than or equal to some little r, where little r is some positive number less than r. Okay, so that's what's going to happen here. So the idea is that you have the complex plane, you have some complex number z naught, and then you're going to have a radius of convergence. Okay, so that means that there's going to be some circle. This is now why this is where all the terminology comes from. If you've ever wondered why it's a radius of convergence. So this is now going to be the set. So let's call this distance here. Let's call that R. And what this theorem is saying is that inside the radius of convergence, it's going to converge absolutely. So for the pink values that I just drew, you get absolute convergence. I'm sorry if this is a difficult thing to see. Hopefully zooming in makes it a little easier to differentiate there. But that's going to give you absolute convergence on that pink set. So that's the interior of the disk. It's going to diverge outside of the disk. That's this red area. Okay, so it's going to diverge outside. What happens on the boundary itself, anything can happen. It can converge, it can diverge, and it's inconclusive. There's no way to tell. And then finally, if I take any disk, so if I had a nice way to draw this, I would do it. It's possible that we're missing some points on the edge here, right? So maybe the part of the boundary is included, part of it's not, but for the orange parts, it's inconclusive. And then finally, if I take any closed disk that has a radius smaller than R, so say I take a set, something like this, centered at Z naught, on the boundary and inside, so inside this black area, it's going to converge uniformly. Okay, so just to recap. It converges absolutely on the pink area. it's going to diverge in the red area. In the orange area, it's inconclusive. And then on the black disk, it's going to converge uniformly. Okay, I'm not going to go through the proof. Notice that, by the way, all of these disks are centered at Z0, where Z0 is this value here in the sum. So Z0 is, that's why it's called the center of the power series, is that all of the stuff literally happens with Z0 as the center of this disk. Okay, but this is, I'll just call this a proposition. I'm not going to prove this. The book goes through a proof. I would encourage you to just kind of read over it and see if you can understand everything there. But I'm not going to take the time to do that in a video here when you can read it. So yeah, so that's everything I wanted to say about power series. In the next video, we'll talk about the root test and the ratio test, and we'll go over a few examples.